Welcome to Lesson 4G, Compressible Bernoulli Equation. In this lesson, we'll derive some compressible forms of the Bernoulli equation, but we'll restrict it to inviscid regions of flow. We'll first derive a general form, and then we'll simplify it for irrotational flow and for barotropic flow. Instead of the Navier-Stokes equation, we start with the Euler equation, where the viscous terms are already gone. We'll use one of the vector equations from the previous lesson. We'll also use the trick from the previous lesson for the gravity term. The algebra is similar to the previous lesson, and you could verify on your own that you get this equation. This is just Euler's equation expressed in an alternate form. I'll call it equation 8, where we're continuing the numbering from our previous lesson. Now let's do some simplifications of equation 8. The first one will be for irrotational, isentropic, steady, and for all these problems, it's inviscid, since we started off with the inviscid Euler equation from the get-go. And these are also compressible flows. These two apply to this entire lesson. Well, the steady flow approximation gets rid of this term, and the irrotational approximation means that vorticity is 0, and that gets rid of this term. From thermodynamics class, you may recall the TdS equations. One of them is TdS equal dE plus P dV, where this V is the specific volume, which is just 1 over density. The other TdS equation is TdS equal dH minus 1 over rho dP. Let's look at this one. We said that the flow was isentropic in our approximation, so the left-hand side goes away. Thus, dH is 1 over rho dP. These TdS laws are written for a system or a material volume. In other words, we're following a fluid particle. Therefore, we can use material derivatives and write this equation as dH dt equal 1 over rho dP dt, following a fluid particle. We expand the material derivative in the usual way by its definition, but again, we're talking about steady flow. So the unsteady terms go away, and the ui on each remaining term cancels, leaving us with del h del xi equal 1 over rho del p del xi. But notice that this term is the same as this term in our Euler equation.
But sir, you have 3 i's in that second term. Doesn't that violate our rules about tensor notation indices?
Yes, I made a mistake up here. We need to use a different dummy index, or repeating index. I'll use J instead of I to avoid having 3 indices that are the same. Thanks for spotting that error, Boris. Continuing, when we substitute this for that pressure term, equation 8 becomes del xi of 1/2 uj plus del h del xi plus del xi of gz all equal to 0. We'll again call uj v squared. Grouping all the terms together, we have del xi of h plus 1/2 v squared plus gz equals 0. As we argued previously, when the gradient of something is 0, that function can't be a function of space, although it may be a function of time. But here we're talking about steady flow, so the grouping of terms in brackets must be a constant everywhere. We'll call this equation 9. This is the Bernoulli equation for steady, isentropic, inviscid, irrotational flow, but compressible. Compared to the beloved Bernoulli equation, we see that it looks very similar, but with P over rho in place of H. Note that specific enthalpy H includes this P over rho term, but it also includes specific internal energy, which must be included when we're talking about compressible flow. Our second simplification will be a special kind of compressible flow, namely barotropic, which means that rho is a function of pressure only. For example, an isentropic ideal gas has density equal to a constant times P to the 1 over gamma, where gamma is the ratio of specific heats, Cp over Cv, where often gamma is K instead, for example in our undergraduate textbook. So this is an example of a barotropic case. We're not going to use this much in this course, so I'll spare you a lot of the algebra. I just want to mention that there are some subset simplifications under this. For the steady case, we get 1/2 v squared plus integral of dp over rho plus gz equal constant along a streamline. We'll call this the Bernoulli equation for barotropic, steady, inviscid flow, but it can be rotational. if it's not only steady but irrotational, we get the same equation on the left-hand side, but now it's constant everywhere. This is the Bernoulli equation for barotropic, steady, inviscid, irrotational flow. This is analogous to the incompressible case, where the left-hand side was constant everywhere for irrotational flow, but constant along a streamline for rotational flow. Number 3, if it's unsteady and irrotational, we have to include the del phi del t term, and the right-hand side becomes a function of time, where we must be careful to define a compressible form of the velocity potential function phi. This is the Bernoulli equation for barotropic, irrotational, unsteady, inviscid flow. In all these simplifications, this integral will depend on how ρ varies with p. Since these are all barotropic, density is a function only of p and must remain inside the integral sign. I typed up and summarized these various forms of the Bernoulli equation. I also typed up these vector identities that we had used. In the previous lesson, we started with the incompressible Navier-Stokes equation and came up with these special cases: incompressible, unsteady, and irrotational, but viscous form of the Bernoulli equation, where phi again is the velocity potential. The incompressible, steady, and irrotational Bernoulli equation, which I like to call the beloved Bernoulli equation, where the sum of these three terms is constant everywhere. And the inviscid but rotational version of this is that the sum of these three terms is constant only along a streamline, but the constant will differ on different streamlines. In this lesson, we looked at compressible flow. Starting with the compressible Euler equation, we derived the compressible, inviscid, steady, isentropic, and irrotational Bernoulli equation in terms of specific enthalpy. It's interesting to note that this equation can also be obtained from the energy equation, or the first law, when the same assumptions are made, which personally I find quite fascinating, that we can start with two very fundamentally different equations, one for momentum and one for energy, yet end up with the same simplified equation. Another case was compressible but barotropic and inviscid flow, where this is our definition of barotropic. And we made these three simplifications. All of them are barotropic and inviscid. This one is steady but can be rotational. This one is steady and irrotational. And this one is unsteady and irrotational. And as I noted, velocity potential phi can be defined for a compressible flow, but only if the flow is irrotational. Most of this course is incompressible flow, but we have these equations at our disposal if we need them.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.